Our third and final speaker of this session before lunch is Nathan Roos, electrified powertrain system engineer of drive system design. He's going to discuss adapting powertrain and fuels decisions to meet emissions regulations through simulation. Just find his thing. You good? You good to go? Yeah, okay.
Okay. The needs of the off-highway powertrains are not currently being met by the simulation and sizing tools that are available. The needs are not being met. Now, there's probably a lot of people in this room that know that and knew that, but that was new to me recently. And I've been in powertrains my whole career. I've done diesel, electric, transit bus. I've done passenger car, battery electric only. Before I even had a career, I was competitively racing solar-powered EVs. So for me to say that the needs aren't being met, I've experienced it. And now I have the opportunity at Drive System Design to optimize powertrains for customers. And it's mainly been using ZeBeyond's analysis tools. It's mainly been on highway. So I understand what a good simulation and sizing tool should be from my on-highway experience. But I think the on-highway world is adapting and deciding. And I think there is information that can be gleaned from the on-highway world to help us in the off-highway world. So I'm going to go through the compare and contrasting on-highway and off-highway, starting with the markets, how the markets are different, the cycles are different, the powertrains are different, and how this leads to we need a different simulation tool. So let's start with the markets. So the on-highway, if you look at product volume and on the spectrum from on-highway to off-highway, we've heard today already that the thousands of combinations at the off-highway. But the on-highway, these are high volume, large engineering teams that do these simulations, often these common powertrains across multiple vehicle platforms. And all of this provides the resources to support new component development specifically for these powertrains. Now, contrast that with the off-highway world, which is a long tail. There's volume there, but each individual product volume is small. So this creates a different world. Lower product volume. These are smaller engineering teams that are working on these powertrains. Very different powertrains across these, and it's unlikely that they're going to develop a new component for such a small volume. They're looking on the shelves. So next, if you look at the cycle, energy versus cycle time, which Ray showed his for off-highway. If you look at the on-highway, the automotive, it's a very defined function. It's transport of the vehicle, what it has to do. And oftentimes the cycle is even given to you by the regulatory body. And then as far as range of what the vehicle is expected to do, there's some variation, but that puts the solution space for the on-highway automotive into a pretty relatively small contained box. Now you compare that with the off-highway world. Cycle times could be anywhere from lawn care, which is minutes or hours, to 24 hours a day in the mining application. Energies are all over the place. So this is a huge solution space with no defined cycles and a bunch of multiple functions. So the on-highway, let's look at the powertrain. What does the powertrain look like and sizing and simulation? So in order to analyze, do the simulation for the automotive, it's pretty straightforward, just literally straightforward. I was at a conference just a couple of weeks ago where the big three automakers basically talked about how they had developed their simulation tools over the past 30 years to analyze this situation, this straightforward situation. Now, compare that to the off-highway. Where do you even start? You know, which one are we going to analyze? What functions? I mean, so the solution space is huge. So when we look at the sizing and simulation, who's even doing this? And what are the simulation tools that they're using now? So through this journey, we were pointed by some people in the industry that you need to talk with AIE. Their engine distributor, Cody's here today. They're doing some of the sizing and simulation by themselves. You know, in this case, it was a prototype hybrid boom lift. So they had added a motor and batteries, added a disconnect clutch, downsized the engine, and what was the simulation tool that they used? Intuition, which is good. You know, it worked for them, but it's not necessarily scalable. You know, this project that they physically built, it's going to be resource intensive, time intensive. It took 2 years to do that, and even at the end of the 2 years, they're not, you know, certain that they've got an optimum solution. They've got something that works. There definitely is improvement to be had, you know, in these powertrains, but this is not as scalable. So at DSD and ZeBeyond, it was like perfect. We have a situation where we can help with simulation. We're going to take our on-highway tool to AIE and help them get to a solution. And they basically said, thanks, no thanks. I don't think that meets our need. It's like, okay, what is your need? This is our need. This is a typical off-highway application. We don't have one function of transport, more like 5 or 6 functions. And then to make things more complicated, you look at the energy distribution of each of these functions on this orchard sprayer example. What's the powertrain? You know, so if you take the on-highway world and you analyze one straightforward, you know, which one do you analyze? You could analyze them individually, which cumulatively takes time. You know, but we started to understand the challenge, and I started to understand the challenge that they were facing. So if you really look at it, this is kind of what the powertrain looks like and how it's different from the on-highway world. But the legacy analysis that was done was actually pretty simple. It's power-based. You add up all the powers, and your one power source has to cover it, so that makes it relatively simple. In addition to that, hydraulics, for what faults, efficiencies they may have, actually simplifies the solution space too. You know, it's like you add up the hydraulics. So it's a very solvable powertrain problem because you're solving in the one dimension of power. The problem with that is that often leads to oversized engines. If you have an oversized engine for its application, now you've entered a lot of emissions challenges that we just heard about. You know, it's like you don't want an oversized engine. And there are efficiency and cost gains to having the appropriate size engine. And in the off-highway world, we know that the emissions regime that you're in, that you have to live in, is determined by the size of the engine. So there's a lot of reasons why we don't want to just do oversized engine. So they want to make this into a hybrid. You know, it's like this is the challenge we face. Once you do that, you introduce batteries into the powertrain. Now it becomes a three-dimensional problem at minimum. Not only is there power, but now there's energy and time. So you can move that power from the engine through the batteries to be across time. You can apply that power across time. You can't use your one-dimensional analysis, and intuition really breaks down at this point because of these multi-dimension problems. On top of that, once you introduce electrification and make it more general, there are multitude of different ways to implement electrification. Do you keep everything that was hydraulic and just stop there? There's different technologies on top of that. So going from energy to the power source to the power delivery to all the OEM or customer functions, which could be anyone from 0 to N on any number of these functions. These are just, list of the possible ones. Could be hydraulic, could be electric, could be a combination of hydraulic and electric. So this is the messy middle, and AIE found themselves right there in that, in between these power source component suppliers and in between the functions that they know they have to size for. So actually it was a perfect partnership where, like, tell us what you need a tool to do for you to make this scalable. If you had to distill it down to one sentence, what would it be? That's what our challenge is. So this is the off-highway need. This is what we need. An accessible tool that allows a small engineering team to quickly get to the leading edge of possible powertrain options for all functions, all cycles, and then clearly show the trade-offs between the cost, size, mass, between all the different power source options, all the different power delivery architectures, and include all the different technologies. That's all we need. So, took that to ZeBeyond because that's the tools that I use for simulation analysis. Like, this is very different than your on-highway tool. It's like, are you willing to make a tool to actually address the off-highway need? I'm pretty sure I've listened, I think this is what the off-highway need is. Are you willing to invest in it with your programmers? And to ZeBeyond's credit, they're like, no, we want to address the off-highway. The off-highway is important. We see it as an important market. We want to do that. So what I will then show is what this tool started to look like. So actual kind of screenshots. But before I show any technical stuff, this is the obligatory disclaimer, which we all collectively sigh and hate disclaimers. It's like, wouldn't it be nice if the situation actually applied to me? Because that's what off-highway wants. They're like, I want a solution for me. So I instead did a claimer. Fortunately, I don't live in the medical or legal or political world, financial world. It's not dependent on the whims of the market or the latest study. This is engineering. This is physics. We can do this. This is calculation. Is it a bunch of calculations? Yes. It's a bunch of calculations, but we can do calculations. We can get you a definitive answer. It's not subjective. This is an objective truth that as long as the laws of physics still apply, we can apply them to these past and energy calculations. So I'm glad I live in the engineering world and work that. Of course, I can make mistakes, but mistakes can be fixed. There probably are some mistakes, but let's proceed with confidence. So this is a tool. This is a little video I'll play, and I'll kind of narrate as I'm doing it. You're going to have lots of projects. Here's some. This is the orchard sprayer example. But the ability to load in functions, all of the functions for the powertrain, is that there's a lot of functions that off-highway has to do. Transport might not even be the main one. And you may want to add one. So you just, add it from a spreadsheet, and you see there. Now, you may know information about these functions. You may know that it's an electric load. I'm going to say it's an electric load. You may know that it is a hydraulic function that I'm not going to be able to change. I'm going to go ahead and make those a hydraulic direct function. But then there might be things that I'm not sure what the answer is. I need mechanical shaft power. Is it better to do that with an electric motor or use a hydraulic one? There's an interaction there. There's a dependency. What the solution is going to depend on the sizing of the relationship to the other cycles, next to it. And you can start to see how you can include series, everything, again, from the architectures from the power source to the power delivery, there are, in this case, 137 different configurations that you can architect getting power to those functions. Now you can start to see how it was kind of an overwhelming problem that the choice that you had. But you may want to change the technology for any one of those architectures. The way it's set up is like an A/B comparison. You know, like here's what we have, here's what I want to compare it with. So you have powertrain A, powertrain B. You want to change the technology? Change the technology. You want to change an architecture and how you deliver that? Change the architecture. And then once you've done all that, you still have variable, what are you optimizing for? It could be cost. Cost is always going to be included. So what are the cycles that you have to complete? How many times you have to complete these functions? What's the cost of your electricity? What's the cost of fuel? But you also have to be able to fit it inside the vehicle. There's mass requirements, there's volume requirements that your powertrain has to meet. There's different things to trade off. So once you have those architectures, which you can toggle through, and you saw toggle through, there's a spectrum from, you haven't even sized anything yet. You just kind of picked your technology, picked your architecture, but there's anything on the spectrum from 100% ICE powered to 100% battery powered. And you can see how the results, how the powertrains change based on the technology you've picked and the sizing that you see. So you can know kind of definitively where you need to be on that electrification spectrum. Then when you get to the end, you get a powertrain. It's like this is good. I've got things sized for my application. I mean, you can even you're not done, but you've got the start of maybe a shopping list that you would go seek the partners, the components to get it. Based behind all this, in the behind the scenes, there's a component library where this is where the technology is that you can select, and you're able to upload, you define. There's a bunch of different inverter technologies. There's a bunch of different motor technologies. Which one is going to be the best? We don't know. Let's look at all of them. If you look at batteries, batteries have different characteristics. Some like to use a whole state of charge. Some like to restrict a state of charge. There's going to be different C rating, which is how much power can be delivered. And that's going to affect, there's an interaction there between the engines that you select. So the batteries that are in your library have an impact on the engines that the solutions present. Same thing with traditional technologies, hydraulic motors, hydraulic pumps. You put them in there. It's like put in, characterized the components, create a good library of components. Your costs may be different. Upload the costs, but you can start to see the path where I see this starting to meet the needs of the off-highway powertrains. So that's basically my conclusion. The needs are, the sizing and simulation needs are starting to be met. You can consider all the details of the application specific. It can be specific for your application. You can consider a bunch of different architectures, and in process of adding more, you can consider all the different technologies. And this isn't a problem that you give your simulation team a question and hope that they come back in a week. You saw how you can toggle through results real time. It's accessible. This is a web-based, which is not your typical simulation tool. This gives you the off-highway powertrain crowd the ability to actually know those trade-offs, unlock the mystery of electrification. You can make the trade-offs. You can see the trade-offs, and quickly adapt and decide. You can see the decisions that you have faced, the trade-offs that you make. Now we can go quickly on the cycles, the iteration cycles, because that's what's needed. You could even take this to your advocacy. It's like, this is what's needed. At this cost of fuel, this makes sense, or this doesn't make sense. Even if this cost of fuel, you can put in those scenarios and get trade-offs, whether you're talking to your customer, whether you're talking to your power source supplier. So with that, I'd be happy to answer any questions.